All right, this is a 2000 level math class, so I want to prove stuff sometimes. And in the last video, I talked about and illustrated with an example this idea that if you have ax equals b, so let's write that down. If you have ax equals b, where A is an m by n matrix, so that means x has to live in Rn, and b has to live in Rm. Then the claim was that the general set of solutions, all x that satisfy this equation, you can find one particular vector that satisfies this equation and then add all the homogeneous solutions. So the solutions to x equals 0. So let me write some stuff down just to try to formalize this a little more. So we could say that the general solutions, we could designate that by a set, right? So there's a set S. And that's the set of all x in Rn such that ax equals b. Where b is a fixed vector and x is sort of a variable here. So let me define another set, H, which is the set of all homogeneous solutions. So I can draw that a little better. So this is the set of all x in Rn such that ax equals 0. So H is for homogeneous. And let's fix P in Rm a particular solution to ax equals b. So what that means is, so that means that a times p equals b, right? And the claim is that S is actually, we could rewrite this S as the set of all things of the form P plus little h, where little h is a homogeneous solution, so it's in big H. Right? And so let's call this set, let's give this set a name. Let's just call this, set T, maybe. Okay. So the claim really is that S equals T. That's just a way to sort of formalize the idea that every general solution, that's everything in S, is of the form P plus H, where H is a homogeneous solution. And right, and so the question is, how do we prove that? How do we like really formally prove? We really have these two sets. We have this set, which is the definition of S, and we have this set. And I want to prove that they're the same set, right? I want to prove that this and this are the same. So the proof, we want to prove S equals T. So how do you prove two sets are equal? Well, this is a standard technique you'll learn in math reasoning, but the idea is that you show that everything that lives in S also lives in T, that everything that lives in T also lives in S. So it's kind of like, it kind of goes both ways. And so that means they're the same set. So the idea is that we're going to show every element of T is actually in S. I don't know why I'm making these fancy letters. Doesn't really matter. T is actually in S. Part of the problem is that I can't write an S very nicely, so I'm doing that to make myself slow down. And then, so what, you know, a way to make that a little mathematical is to say that if X is in T, that implies that X is in S. Or another way to say this is that T is a subset of S, because I mentioned this subset notation before. And then B, we want to show that every element of S is an element of T. Every element of S is actually in T. And so again, that's sort of saying that that's proving the logical statement X is an element of S implies X is an element of T, or that S is a subset of T. Okay, so this is what we want to prove. This is a standard proof strategy when showing two sets are equal. And so let's do that in turn, and it's not too bad. So let's start with A. Let's prove A. So what you do is you basically start with an element of T, right? We want to start with something in T and show that it's in S. So let me just to make it a little more specific, let me just say like X naught, let X naught be an element of T. What that means is that, you know, the definition of T was up here. So to be in T means it's of the form P plus H. Thus, X naught is P plus H for some choice of H. Little h and big H. Right? That's kind of just what it means to live in the set T. And we want to show that something like this also lives in the set S, so it's actually a solution of AX equals B. So yeah, we want to show that AX naught equals B, because that by definition means that X naught is an element of S, the solution set S. So how do we prove that? Well, let's just compute AX naught. And you'll see it's not too bad. Compute AX naught. And by compute, I mean, let's just plug in P plus H. I mean, compute sounds weird when this is such an abstract discussion, but I just mean like plug in P plus H for X naught. And then we have this nice property that matrix multiplication actually is linear, is what it's called, that it distributes over addition. So it respects addition, right? So that's AP plus AH. But by definition, we said, if we go all the way back up here, that AP is B, and that the idea of living in H is that A times something is 0. So in fact, once we have something like this, this equals B by definition, because that's how we chose P. And this equals 0 because H is a homogeneous solution. Little h, the vector little h is a homogeneous solution. So AX naught is actually B plus 0. AX naught is B plus 0, which is just B. And there it is. We just showed AX naught equals B. It was very easy, right? It's basically saying, what we're really saying is that if we add a homogeneous solution to a particular solution, it's still going to be another particular solution, because the homogeneous solution sort of doesn't change. It still gives you when you hit it with A, you just get 0. So it doesn't change the value of A times that vector. So you still get B. That's kind of what this argument is doing. And so therefore, we just showed, those 3 dots sometimes are read as therefore, we just showed that X naught lives in S. Okay, so that's half the proof. Okay, now what about the other direction? So that's, pause if you need to think about that and go through the logic, but we just showed this stuff up here, that we just showed this statement or this statement, that T is a subset of S. So T was a set of particular plus homogeneous solutions, and we just show that that's every quote particular plus homogeneous solution is a solution of the original equation, matrix equation. So now we want to go the other way. Let's pick another vector. Let's just say x1 is in S. So by definition, that means ax1 equals b, right? And we want to somehow show that x1 is in T. We want to show, let me just write, we want to show again. We want to show that x1 is of the form p plus h1. Let me say, maybe I should have actually said, sorry, up here in this proof, maybe I should have really just put subscripts like h naught everywhere, just to be like a specific vector. It's not that important, but I just want to be, sometimes when you have variable, like an x is like a variable vector, it's nice to give it subscripts, and an h is sort of like a variable vector too, because in the definition of h up here, well, I'm using little h basically in place here. So anyways, I'm just going to put subscripts to make it clear that these are specific. So we want to show that x1 is p plus h1 for some h1 living in capital H. So the vector h1 living in capital H, which is basically for some homogeneous solution. This is very formal ways of saying these things. Okay, well, it's a little bit hard to do that directly, but let's notice something. So we have ax1 equals b, but also AP equals B, because P was chosen as this particular solution, right? And that means AX1 minus AP, sorry, is 0. I'm basically forgetting about the B and just kind of connecting these two directly. So AX equals AP, so AX1 equals AP, so AX1 minus AP equals 0. And again, we can use this sort of this nice distributive linearity property to say that's true. Factor out the A times x1 minus p is 0. But that means that x1 minus p is a homogeneous solution. And x1 minus p is a homogeneous solution. It lives in capital H. Is an H, which means that x1 minus p equals some element of H. And so let me just say i.e. x1 minus p equals h1 for some h1 in capital H. And then we're almost done, because we just add the p back over the other side, and that means that x1 equals p plus h1, where p is this particular solution and h1 lives in H. And by definition, this is something that lives in the set we call T, right? T was the set of all things of the form p plus h, particular plus homogeneous. And so, in fact, therefore, x1 lives in T. And that's what we wanted to prove. Right? So we started with, in part A, we started with an x naught in T and showed that it lived in S. And then in part B, we started with an element of S and showed that it lives in T. And that proves both ways. So we're done. S, the set S equals a set T. And you could write QED if you'd like to the end of the proof, which is Latin quota rod demonstrandum. That was supposed to be proven. Or mathematicians just write a box, sometimes shaded in. Just say that they're done with the proof. Awesome. Hey, look, we proved something. Very fun. Okay. I'll stop.